In the last lecture, I started talking about the hydrodynamic interaction, because in the Rouse model, we had only chain connectivity. In this Rouse model, we had talked about only chain connectivity, essentially a single chain in infinitely dilute situation. And then we made predictions like the diffusion coefficient being 1 over n, specific viscosity becoming n square, which were different from what we would get from Einstein's law by generalizing Einstein's law for coils, polymer coils. You would get a D going like 1 over R. That means it'll go like 1 over n to the nu, not simply 1 over n. And here it'll go like n to the 3 nu instead of n square. So there are differences between this theorem and between the Rouse model, which accounted only for chain connectivity. We did not consider anything else. And we wanted to look at a dilute solution. When you look at a dilute solution, the polymer chain is not alone. It is not in vacuum. It is in a solvent, but some viscosity eta naught. Again, when we go back and look at the comparisons, right here, eta naught, that's the viscosity of the solvent, is appearing for the diffusion coefficient in the Einstein's generalized Einstein's theorem. Now, if you take the Rouse model, the viscosity of the solvent is not appearing in here. Therefore, we need to go back to Rouse model and try to think about where does the viscosity come in. That comes in through the solvent. Solvent has viscosity. And as I talked about before, when every monomer is beginning to make a motion here, it creates a force. That force will travel through this liquid and affect the motion of another monomer. And that another monomer could be any of these monomers on the chain. It could be this, it could be that, it could be that. And when this receives the signal from this monomer, it will also create a force field, and that will move through the solvent and affect the initial monomer, next monomer, another monomer, etc. So for example, here, when it moves, it can affect this monomer, it can affect that monomer. And this is called hydrodynamic interaction. And this hydrodynamic interaction was included in describing the polymer dynamics by Zimm. And we call this to be Zimm model. In fact, the same model was described even more clearly by Kirkwood and Reisman about a decade earlier. So nevertheless, all books will tell you it's the Zimm model. Realistically, we should be giving proper credit to Kirkwood and Reisman. So we will call Kirkwood-Reisman Zimm model, or for textbook case, in order to make it simple, we'll call it Zimm model. So basically, the difference between Rouse model and Zimm model is in Zimm model, we will include hydrodynamic interaction. And I must tell you right away what this hydrodynamic interaction is, because probably some of you already know, but let me tell you for benefiting the rest of our discussion. So if you take a liquid, right? If you take a liquid somewhere, this is a liquid, suppose, and which has a viscosity eta naught. Suppose I put a force at some location here. I exert a force at location there. Let me denote that location to be R prime. R prime could be, that location could be here, 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 anywhere, right? Then I have another location here where I'm going to monitor, I'm going to say somewhere here, I'm going to monitor the velocity at that location. Let me say V is the velocity of the fluid at that location R. And how is the force exerted here going to influence the velocity at this location. Okay. In order to do this, we need to solve, in order to get that expression, that is right, there is going to be a wave coming here, and the wave, when I'm looking at the velocity here, that wave can come from here, 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 everywhere, right? Everywhere from in this fluid, I'm going to get a velocity. And then the question is, how are we going to do this? We need to solve an equation for this fluid, equation of motion for the fluid. If we treat the fluid as a continuum, right? If we treat solvent as a continuum, that means what? We do not consider molecular structure of the solvent molecules. Suppose I have cyclohexane, we don't look at that length scale of molecular length scale of cyclohexane, but we look at macroscopic length scale of the whole liquid. If you do this, we have Navier-Stokes equation. To make it easy, because when you have Navier-Stokes equation, it's actually nonlinear, right? So we are going to be specializing linearized Navier-Stokes equation. That means we are not interested today about turbulence, et cetera, right? We are interested in very weak flows, right? So linearized Navier-Stokes equation. That equation looks like this. Rho 0 dV at some location R at time t by dt, right? And negative eta naught del square, right, in three-dimensional second derivative, V or T, okay, plus gradient of a pressure at the location R and T, and that's equal to any external force at that location R and T. So this is external force like gravity, or if it's a charged molecule, an electric field that would impose, right? This P is pressure, hydrostatic pressure at that location. And this is the density of the fluid. And eta naught, you know, that's the shear viscosity, right? But in general, we are interested in very long time behavior because, right, in our case, the relaxation time, as we pointed out here, you can make a guess. If you use, right, if you use a Rouse model, it goes like n square, molecular weight square. That means the time scales are much large. The time scales are much large, but the structure of this equation, look at this, V is displacement divided by time. Here, dV by dt, that's a displacement divided by time square, and time is very large. So for all practical purposes, we could ignore this inertia term. Ignore inertia for practical purposes. But if you care about high frequency, that means very short-term behavior of polymer dynamics, then you have to keep this, right? But we are going to ignore this, okay? This I call, if you do that, this is called zero frequency limit. Low frequency means very long times, right? So this is zero frequency limit. In that limit, then, I have a simple expression, del square V grad P is equal to F. Right. And I'm also going to assume the liquid is incompressible. Assume solvent is incompressible. Okay, incompressible. So if you do this, then we can solve this equation. Exactly. Okay. And the expression turns out to be like this. I'm not going to go the derivation, but I'm going to introduce the language and give the result. Because that can be mathematically involved. That's not our purpose here, right? And it turns out, when you look at this one, the general structure is more like a diffusion equation, but except now it's going to be a tensorial character because of all these gradients, etc. Right? But nevertheless, the answer is this. If I want to know the velocity at some location R, okay, and it's a zero frequency, so time is very large, so I don't have to worry about, well, I can put a T if you like, right, VRT. And that's what I'm interested in. And this is going to depend on force at some location, any arbitrary location. Force at R prime, right? So how does the force at R prime propagate through the liquid to give me the velocity? And that's the question. And the answer is the following. If you do this, the answer turns out to be, yes, you integrate over dr prime, right? Dr prime, that is, this source could be anywhere. Source of the force could be here, 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 anywhere, right? And there is a key which converts this force at this location into velocity. That I'm going to write to be with this term. Let me use a different color. 1 divided by 8 pi eta naught. Okay, eta naught is the viscosity of the fluid, right? Eta naught. And then I have this quantity, R minus R prime modulus, times a tensorial quantity, which is like this, unit tensor plus R minus R prime. It's in the handout, okay? R minus R prime divided by R minus R prime modulus square. That's a tensor. This is called Rouse tensor. Okay, right. This is called Rouse tensor, and let me give a symbol. Instead of writing this whole square bracket again and again, let me give a symbol to that one to be G R minus R prime. That's my Rouse tensor. But the key attribute of this Rouse tensor is the fact that it looks like 1 over R minus R prime. There's a tensorial nature, right? Depends on what angle the force is attacking at a particular location in here, right? So that's a small numerical factor when you average it out. But the key feature is this is 1 over R minus R prime. Whenever you have 1 over R minus R prime, that means there is a long-range interaction. That is, this fluid element, suppose I have some boat in this lake somewhere at this location, although another boat is far away, still I will feel the effect. It's called a long-range interaction, long-range correlation. Right? And we had seen this even in equilibrium. If we took a Gaussian chain, we had long-range correlation in the monomer density. One monomer knows that it is connected, it's part of a chain, and it's, it is influenced by another monomer, although it's far away along the contour. Similarly, here we have this G R minus R prime to be long-ranged. long-range interaction. Unlike the chain connectivity, where we talked about long-range interaction in equilibrium, here we have long-range interaction in terms of dynamics. It's a hydrodynamics. So how do we deal with this? Again, it is very difficult to do an exact calculation. Not only difficult, it's impossible to do exact calculation. So what people do is they do what is called pre-averaging. All right. That means that going back here, we assume when the hydrodynamic interaction is operative, we assume that that interaction is so quick, so fast, that for all practical purposes, the chain conformation is fixed during that correlation. When this sends a wave, this receives so quickly that the conformation has not changed. Now, this is called a pre-averaging approximation. So if you do pre-averaging approximation, if you do this, what is this? That is the hydrodynamic interaction. Let me write hydrodynamic interaction, right? That's HI, right? Travels so fast that chain conformation has not changed. Okay, that's the meaning of this pre-averaging approximation. You will read this in books. That means you are averaging the hydrodynamic interaction with keeping the conformation same. Okay, so what's the consequence of this? The consequence of this is the following. Let me go back to remind you about Rouse equation. So this gives me Zimm equation. Okay. And I'm going to simply write this instead of deriving it. If you derive this, it will take a considerable amount of time. And so it's not necessary for this particular course. So let me just quote this. Again, I'll remind you with the Rouse equation, right? The Rouse equation, we had something like this, right? We had the friction term, and then we had the connectivity term, and then there's a random force term. And you know what P is? P is the Rouse mode, right? P is this Rouse mode. These are the meanings of various modes as we discussed. Right? So we have same equation as this, which I'm going to write in a minute. But on top of that, we have hydrodynamic interaction. So I'm going to write Zimm model in terms of the Rouse mode variable P, because those vibrations on the chain, they are the same, you know, whether it's a Rouse model or for an entangled system or for with the hydrodynamics, with have excluded volume interaction, what have you, but we always have Rouse modes or normal modes, which we call Rouse modes. So although I'm going to talk about a Zimm equation, I'm going to be writing this equation in terms of Rouse modes. Right? So let's go back here. Going back to, excuse me, what I said before, there is a friction term, which is D or P or hat P at time t divided by dt. That is coming from friction. Plus, and then we have coming from chain connectivity, we had something like this, 3 pi square kBt divided by L square, P divided by N square, right? And then we had RP at T, and that's equal to the random force acting FP hat at T divided by friction coefficient. This is a bead friction coefficient, right? This is what we are. This is so far Rouse. Now, when we put hydrodynamic interaction with a pre-averaging approximation, what happens is we can derive this. If you derive this, you get additional factor here, D, which depends upon the Rouse mode P. Okay, so that's a modification we get. But this is coming from hydrodynamic interaction. Right? This is coming from hydrodynamic. And what is dP? Right? And a dP is equal to, right, 1 divided by zeta plus, I'll give you the answer, plus 1 divided by 3 pi cubed square root eta naught L, and then N over P power half. Okay, that's what happens. So dP depends upon the P variable also. Okay. So this is the Zimm equation. So we have the friction, chain connectivity, and then that is because of coupling among various monomers, long-range coupling among various monomers, we get this factor, which depends upon molecular weight too, molecular weight and Rouse mode. And this is a random force. And P is your Rouse mode variable. And zeta is segment monomer friction coefficient. And eta naught is shear viscosity. And T is temperature. L is your Coulomb length. So we have that. Okay, as soon as you have this, we can write the relaxation spectrum. Right, the relaxation spectrum is what is Zimm, therefore, by inspection, because here is a time, and then you take all these factors, and that is a reciprocal of time. Therefore, Zimm spectrum, Zimm relaxation spectrum is tau P is equal to, you can tell right away, right? That will be 1 divided by this quantity dP, and then everything else you had before, right? That is N square, L square, divided by, going back to your earlier notes, 3 pi square KBT and 1 over P square. Okay. But please notice that dP is 1 over, if this is important, right? Look at this. Suppose that this is hydrodynamic part. If this is important compared to this, then we have dP is 1 over root of P. Therefore, 1 over square root of P becomes square root of P in the numerator. So the Pth mode relaxation time is not 1 over P square anymore, but it's 1 over P power 3 halves, 3 by 2, right? In the Zimm. In the Rouse, suppose this is not important, suppose, no hydrodynamic interaction at all, then this gives you your Rouse spectrum, because when dP is simply 1 over zeta, this is not important, 1 over zeta, this becomes zeta times that. That's precisely what we had for Rouse, obviously, because that's how we built the theory here, okay? So if there is no hydrodynamics, if I'm repeating, if no hydrodynamic interaction, right, we get back Rouse spectrum. This means, right, in the literature, people call this to be free draining limit. If you take books, right, they call this as free draining limit. If you take books, right, they call this as free draining limit. If you take books, right, they call this to be free draining limit. If you take books, right, they call this to be free draining limit. If you take books, right, they call this to be free draining limit. If you take books, because there's no hydrodynamic interaction. It's just a free draining. The liquid is passing through, right, without any interaction. Free draining limit. This is the language that people use. Okay, basically it means there is no hydrodynamic interaction. If hydrodynamic interaction dominates, right, we get Zimm. And of course, this will be called opposite of free draining, and we call this to be a non-free draining. So, oops. Now, given this, for a Gaussian chain, we can calculate tau p. What is longest time? Well, in general, if this dominates, right? This dominates. So I can, if this dominates, then I can ignore this term. Then what happens is that tau p, therefore, tau p in this case goes like, we can copy this, right? We can take these things and put it back in here, combine with these terms. If you do this, you get eta naught L cubed as given in the handout. Square root of 3 pi kBt, and the key issue attribute is n over p or 3 halves. Please notice it. In the case of Rouse, you will get n square, n divided by p power 2. But for a Gaussian chain with hydrodynamic interaction dominating, the pth mode relaxation time goes like 1 over p power 3 halves. And in terms of a molecular weight, it goes like n power 3 halves. Okay. Therefore, the longest relaxation time would be p is equal to 1 case. Right? When p is equal to 1, we have the longest relaxation time. Therefore, the longest relaxation time turns out to be for Gaussian chains the longest relaxation time right, is tau is equal to, and I'll put this subscript Zimm. Okay, that's the longest relaxation time for the Zimm model with the hydrodynamic interaction. That turns out to be, you can take this and put p is equal to 1. Okay, so what you get is eta naught L cube divided by square root of 3 pi times kt n power 3 halves. Okay, so I could, yeah, so let's do that. Okay, let's do that. If you do that, again, eta naught L cube at the risk of repetition, 3 pi over kBt, and you know the value of 3 and pi, n power 3 halves. So this is a punchline. This is the important quantity. It goes differently. Okay. And what we say is, what is important? It depends on viscosity, it depends on temperature, and depends on molecular weight. See, that's the key message that comes out of this calculation. Now, I can also rewrite this. If I take, this is a Gaussian chain, right? For a Gaussian chain, use Rg, you know that, right? Rg is number of Coon segment length square divided by 6 square root. That's my Rg, right? Use this Rg, of course, for Gaussian chain. We're talking about Gaussian chains. If you do that, your Zimm time goes like Zimm is equal to, right? You plug in, right? Square root of n is proportional to Rg. So n power 3 halves is proportional to Rg cubed. Put all these numbers, square root of 6, root of 3 pi, etc. If you do that, you get some number like a 4.8. It's a good number to remember. Yeah, it's a good number to remember, around 5 as a prefactor. Eta naught by kBt Rg cubed. Okay. So I could write this to be eta naught by T n power 3 halves, but I could also, this goes like eta naught by T Rg cubed. This is 1000. Okay. Although I derived this for Gaussian chain, this result is true in general. That is, if I put extra volume effect into Zimm model and you calculate this, semi-flexible chain and calculate this is true in general for all new values. Nu is size exponent, right? Half, 0.6, 0.8, whatever values there are, this formula is true. So basically the relaxation time, Zimm relaxation time goes like Rg cubed. Okay. So now what I can do is, using this Zimm equation, we can make some predictions. We can go and solve this equation. Very much what we did for Rouse. If you do this, I can show in general we can show the following. Suppose I label one monomer, okay, the mth monomer, Rm at T minus Rm at some earlier time square, okay, average. Please remember, in the case of Rouse, going back to this table, in the case of Rouse, we had this problem, right? We found out we found out half, that's a signature, right? The mean square displacement of a monomer went like square root of T. If you do spin echo experiment or experiments of that type, if you're able to monitor the monomer displacement, label the monomer displacement, went like square root of T, and that was responsible in giving you this incoherent structure factor where the decay rate was k to the 4. This was a Rouse. Analogously, I can show for our case, for the Zimm case, if you do the calculations, you can show that this goes like T power 2/3. Okay, it goes like T power 2/3. Then I can look at the center of mass calculation or center of mass at time T, similar to what we discussed for Rouse. Square. This is equal to, it turns out, for long enough times, 6d center of mass time T, if T is larger than tau Zimm. Because you always have to compare. When you say time, you have to compare, are we talking about time longer than the characteristic time of the problem or not? If the time is longer than the characteristic time, then it will undergo Einstein's diffusion, and therefore there's a diffusion coefficient. That diffusion coefficient turns out to be, when you calculate it, that turns out to be 1.51. Okay, a number, I remember this, roughly 1.5 kBt for a Gaussian chain. For a Gaussian chain, 6 pi eta naught Rg. Now, we can observe this is 6 pi and 1.51, right, by defining another radius. right? I can write this 1.51 divided by RG as another 1 over some radius. Okay, so I will write this to be KBT divided by 6 pi eta naught RH. Okay, I will write RH. Or this is called hydrodynamic radius. Okay. This is more like a Stokes-Einstein, going back to, because we always wrote, right, in Stokes-Einstein for a Brownian particle, we found what? We found 6 pi eta naught, 1 kT by 6 pi eta naught times radius of the rigid sphere. Instead, we could write in the same form, right? KT by 6 pi eta naught RH. But please notice that RH is related to RG. RH is simply proportional to radius of gyration. And radius gyration of this coil, in this particular case, Gaussian chain, it will be square root of molecular weight. Right? This is fantastic because this is what we anticipated. Going back here, we wanted D going like KT by 6 pi eta naught some radius. That radius will go like n power nu. Therefore, D will go like 1 over into the nu. That's exactly what we get from Zimm model. Okay, we get that one. So that's beautiful. Right? So as soon as you put in the hydrodynamic interaction, you get Einstein's result. So Rouse in dilute solution is not applicable. The Rouse model that gave without hydrodynamic interaction is not useful to treat dilute solutions. Now let me add one more comment about viscosity change. Right? The viscosity change, it turns out using Zimm model, eta minus eta naught divided by eta naught C. That's basically dilute solution. That means this is intrinsic viscosity. This is intrinsic viscosity in dilute solutions. This is equal to, this is the gas constant divided by molecular weight over eta naught and summation over P, these are Rouse modes, tau P. Okay, and we know what tau P is. And R is gas constant, Boltzmann constant times Avogadro number, M is molecular weight. Okay, and tau P, we worked it out. Tau P, it turns out to be right here. Tau P is, right, tau P goes like 1 over n power 3 halves. Okay, n power 3 halves. So I go back here, I have tau P is n power 3 halves, and here is a factor of n. So overall, it turns out to be n power half. You can do the summation over P. We can do that mathematically. That's not a problem, right? So this means, right, this goes like molecular weight power half. But in general, we can write this to be 3 nu minus 1, where nu is a size exponent. For a Gaussian chain, nu is equal to half, 3 times half is 3 halves minus 1. So square root of m. Okay, and that is, right, that is a change in viscosity due to polymers. And this is also in agreement with Einstein. Because we talked about this already, with some prediction in agreement with Einstein. Okay, let me tell you again. So we went back to the summary here, and we said eta naught, eta minus eta naught went like n power 3 nu, because it's a number concentration. But we write in terms of monomer concentration, I'll multiply by capital M and divide by capital M. So that will be concentration, monomer concentration times n power 3 nu minus 1. That's what we have. Because here we have C, monomer concentration, and the denominator, when I bring it to the right-hand side, I'll get monomer concentration power m to the 3 nu minus 1. This is really fantastic. So this is great. We have gotten that. Okay. So now, very quickly, in the rest of a few minutes, and I like to make a comparison between Rouse and Zimm. So let me open, right? Here is a comparison between Rouse and Zimm. This is in dilute solutions. Okay, here is Rouse, and this is Zimm. Okay, here no hydrodynamic interaction, and here hydrodynamic interaction. Okay, that's what we do. And then Rmt minus Rm0 square, this is monomer, goes like square root of T. Here it goes like T to the 2/3. This means incoherent structure factor, which we talked about before, structure factor, right? That goes like a S incoherent K T, that goes like e to the minus k to the 4 T, square root of T, and their decay rate goes like k to the 4. In contrast, what we have is, it will go like e to the minus k cubed T squared, k cubed T power 2/3. That's the way it turns out, right? Because you can see it goes like monomer displacement goes like T to the 2/3. Then this power, K power should be K square. It should go like a K square times a T to the 2/3, and that's what you get. This means that the decay rate now goes like K cubed. This is an important distinction, right? This is, you can observe this experimentally. In a Zimm dynamics, local, the incoherent structure factor goes like K cubed. If it were Rouse, right, it will be K to the 4. And then let me go to next quantity, R center of mass T minus R center of mass at an earlier time square goes like 6 times D center of mass times T for long enough times, and D center of mass goes like, I'm repeating myself, K B T over zeta, and going back to our notes, that goes to T divided by N. But instead, here we get T divided by viscosity times Rg. Okay, it goes like N to the minus mu. Okay? And again, the change in viscosity by eta naught to C, the way we wrote for Rouse, M eta naught, summation over P, tau P divided by 0 frequency limit, 1 plus I omega tau P, right? And then here tau P goes like say N squared, N over P squared. And here tau P goes like N over P power 3 nu. Okay. And the change in viscosity, it goes like N, and here it goes like N to the 3 nu minus 1. So these are the differences. And this is the right-hand side column is true for any value of nu, and this is the right answer. So this is in dilute solutions. All of them are verified. It is right in dilute solutions. Because you must have hydrodynamic interaction. Okay, I like to take a pause. I think let me stop sharing here. So far, we have been comparing between Rouse and Zimm. Please remember, the Rouse model was invented for single chain dynamics. And what we have shown here is that it is not applicable in dilute solutions because it gives all wrong predictions. The main reason why it fails in dilute solutions is it does not include the effect of hydrodynamic interaction in its description. But once you include hydrodynamic interaction, you get all correct results, which are all completely consistent with Einstein's predictions, as well as experimentally validate. Then you wonder, why do we talk about Rouse model at all? Why do we have to do this? One reason is that's the first step we have to do, because that's the way we want, how we incorporated chain connectivity, right? That's one reason. Another reason is a little bit more profound. Let's explore experimental conditions when this model may become relevant, right? One possibility is completely get rid of solvent. If you get rid of solvent, there is no hydrodynamic interaction, okay? That's a possibility. Suppose I have a melt, maybe there are situations where a Rouse model may become applicable, maybe. We'll see. We'll see in the next lecture. But today, even in solutions, is there a condition where hydrodynamic interaction can be ignored? Is it possible? That's the question. That takes me to the following topic. I want to talk about, consider semi-dilute solutions. The dynamics, polymer dynamics. I like to look at polymer dynamics in semi-dilute solutions. Let's think conceptually. So here is a polymer chain, say one chain in dilute solutions, right? And we know that there is hydrodynamic interaction everywhere, right? We know that this is interacting here, and here is interacting here, and things like that. That's hydrodynamic interaction, right? This is HI. Now let's see what happens if we add more and more polymer chains into the system. That means I'm going to increase polymer concentration. What will happen? What will happen likely, right, is chains will interpenetrate, of course. As you know, right, as you know from previous lectures, the above overlap concentration, chains will interpenetrate. So maybe a second chain may come around here due to interpenetration. If this happens, look at this cartoon, right? I have direct hydrodynamic coupling between this monomer and this monomer. Now, due to the interception by another chain, that hydrodynamic coupling is reduced because this intercedes the message sent by this monomer to this monomer is now intercepted by another chain. Therefore, this monomer does not get that message, right? This is screening the hydrodynamic interaction. Just exactly the way we talked about screening of extra volume interaction. Remember when the chains interpenetrated, the extra volume interaction, intra-chain extra volume interaction was screened out. In a similar way, the intra-chain hydrodynamic interaction, which is also long range, 1 over r minus r prime, and that's getting screened. So the consequence of this is the following. The consequence is, to begin with, apart from 6 pi's, 8 pi's and everything, tensorial character, to begin with, we have 1 divided by eta naught times r minus r prime. This is the hydrodynamic interaction, full-fledged hydrodynamic interaction, was in tensor. It's not a tensor anymore, but I'm writing only the key aspects. Going back here, right, I'm writing there's only 1 divided by r minus r prime, 1 over eta naught times r minus r prime. That's my long range interaction, hydrodynamic interaction tensor, right? That's what I'm writing. Okay. Now, when I increase the polymer concentration, due to this interception and intermingling of all these chains, this I can show how this happens. This turns out to be, it turns out to be 1 divided by eta naught r minus r prime times, sorry, I didn't write it correctly. 1 divided by eta naught r minus r prime times this quantity, an exponentially dumped quantity, which is 1 minus r prime divided by a length, characteristic length, which is a measure of how the interaction gets screened. So I'm going to write this to be CH. This is called hydrodynamic screening length. CH is called hydrodynamic screening. Okay. So that means when I increase the concentration of the polymer, this 1 over r minus r prime gets weaker. The long range interaction is essentially killed. If a hydrodynamic screening length is short, then it is as if there is no hydrodynamic interaction. That can happen if the concentration is high enough. If the concentration is high enough, that can happen. And we can show, I will not go through the derivation. We can show that this hydrodynamic interaction or hydrodynamic screening length is proportional to the equilibrium screening length. And this is correlation length of a monomer concentration. Correlation in equilibrium, correlation length of monomer concentration okay, which we were calling to be mesh size. Remember this? So when they are interpenetrating, when the chains are interpenetrating like this, right? We were calling this to be, this is mesh size. And you know that mesh size, according to the derivation we did before, it's concentration power minus nu divided by 3 nu minus 1, going back to previous lectures. Okay, nu is a half for theta conditions. For good solvents, it's 0.6. You know, put that number, you know, we went through this before, and we had experimental validation. And we can show the hydrodynamic screening length is proportional to this. Only the prefactor is different, right? This means what? As you know, when you lower the concentration, if C is small, this screening length is very large, right? Look at the negative sign, right? 1 over C. When C is small, screening length is very large. When the screening length is very large, then e to the minus 0, right? That means at a low concentration, it is hydrodynamic, full-fledged hydrodynamic interaction, because this term, e power 0 is 1. You get back this dilute solution limit. But when you increase the polymer concentration, increase more and more and more, what will happen is the psi becomes smaller and smaller. When psi becomes smaller, e to the minus a large number. Psi is in the denominator of the argument of the exponential. When this is small, this becomes large. The negative sign, this becomes 0. So basically, this gets wiped out. So the hydrodynamic interaction gets progressively wiped out by screening, by intermingling of the chains. Then what we expect is this. Okay, if that's the case, maybe, and it turns out to be the case, we'll get back Rouse model to be valid. all right? Because if there is no hydrodynamic interaction, we'll have Rouse model, because that's how it was built in, with one significant caveat. Rouse model will tell you change in viscosity is proportional to the concentration because it was a dilute limit. But what we are guessing is the Rouse model may become valid if the concentration is high enough. If the concentration is high enough, due to the interpenetration of the chains, there will be a different concentration dependence. The only effect that is valid from Rouse model in semi-dilute conditions is a molecular weight effect, because if there is no hydrodynamic coupling, only the friction coefficient matters in terms of the relaxation time, etc. But the concentration dependence will be different. And that's what we are going to talk about next. So what we expect, therefore, what we expect based upon this hydrodynamic screening. So let me give a title for this. This is hydrodynamic screening. This is hydrodynamic screening. What is the main consequence of this? The main consequence that we are guessing is, here is the Zimm, and I increase the concentration of the polymer. C is increasing, and as a consequence of C increasing, screening of hydrodynamic interaction. That means, therefore, I expect, right? Therefore, I expect Rouse. I would say Rouse as far as N dependence. Okay, that's what I would expect. Therefore, we expect this. Okay, given this, then we are in a good position to look at lots of quantities, right? Lots of quantities. Before I do this, let me remind you, going back to simple particles, let me remind you, suppose I have, okay. So now the question is, how are we going to describe? How are we going to, therefore, how are we going to do, how are we going to describe the crossover between these two limits? Okay, that's the question. How are we going to do that? Okay, so let's look at, for example, look at suspensions. For example, consider a suspension of particles, spherical particles. Then if you look at the viscosity change, that's equal to, you guys know this, right? Some K1, some constant volume fraction. That's Einstein, right? Eta naught minus eta naught by eta naught is equal to 5 halves. K1 is 5 halves, for example, times the volume fraction. And then when you want to look at a higher concentration, a little bit higher, the additional term will come in, K2, 5 square, plus K3, 5 cube, plus etc. Right? And a K2, people calculated this with a tremendous amount of effort, 5.2, and K3 is equal to 6.4, etc. You can calculate it. But the numbers, K1, K2, K3, they will all depend upon the specificity of your system. For hard spheres, you have this, right? If you have flexible chains, you will have something like this, some numbers like this. But nevertheless, in general, right? In general, we could write this to be eta minus eta naught by eta naught to be some function of n over v volume fraction, right? It's a function of phi. There's a phi term, phi square term, phi cube term. Phi, what is phi? That's n over v r cubed. So that's a volume fraction. Okay, that function is a representation of all these numbers, K1, K2, K3, etc. Similarly, for polymer solutions, we could write eta minus eta naught divided by eta naught to be equal to some function for the viscosity as of what is the variable here, right? We know that, right? C n over v, right? We know that n over v. This turns out to be n m over v, right? R cubed by m, rg cubed by m, right? And n m over v is c. This quantity is 1 over c star, c by c star. So we could write this as a function of c by c star. Okay? We could do that. So viscosity change is some function of c by c star. C star is an overlap concentration, right? This is overlap concentration. Okay, so now the question then is the following. In the literature, right, people look at it also in a different way for viscosity, classically. But in modern times, this is the way we describe. Classically, if you take earlier books and earlier papers, what you see is this. Just like the way we did before for polymer solutions, eta, right, minus eta naught by eta naught is, remember, intrinsic viscosity times concentration. Okay, and it's, right, that's what we calculated so far, right? When we went back and looked at this intrinsic viscosity, for example, that's the way we defined. In a dilute solution limit, this intrinsic viscosity is in the limit of C becoming very small, eta minus eta naught by eta naught. Okay. But when you have interactions between several chains, when you increase the concentration, what you get is you get a term like K2 intrinsic viscosity times C squared. And then K3 intrinsic viscosity 3 cubed, C cubed plus etc. So you could also write this to be F eta intrinsic viscosity times C, some function where you absorb all the K1, K2, K3, etc. into this function. This is the same as what I have written in here, C by C star, right? That means what? That means 1 over C star is like intrinsic viscosity. This form is same as this form, all right? That means I'm writing F eta of intrinsic viscosity times C. That means intrinsic viscosity is reciprocal of C star. This implies intrinsic viscosity is 1 over C star. So sometimes people cannot identify what the overlap concentration is because it's very difficult, right? Overlap concentration is a geometric object. That is a concentration at which the chains are just about to touch each other in a close packed form. That's very difficult to determine experimentally. But if we measure intrinsic viscosity, then that will be a measure of C star. And that's the relationship. Okay, it's a very useful relationship. So you could combine your scattering experiments with rheology, viscosity measurements, for example. Okay, but nevertheless, the key point is this quantity. That is, this is a function of C by C star. Okay, now I'm going to illustrate one example of how we are going to get this a crossover. I'm going to show one example. Okay, one example is this. Okay, so I know right? I'm writing this quantity. I'm writing eta minus eta naught by eta naught is equal to some function. I'm repeating myself. C by C star. That's equal to, right, some function. C star, you know, that is molecular weight or depolymerization. Remember that? C star is one. C star goes like, right, n power 1 minus 3 nu. So this will become, right, remember C star going back here, n power 1 minus 3 nu. You know that. So 1 over C star would be n to the 3 nu minus 1. Okay, remembering that, going back to overlap concentration, that's what you have. And the question is, how are the high concentration limit, right? When, okay, we know for C by C star is less than 1, that's a dilute limit. We know that this quantity is intrinsic viscosity times concentration. We know that already, because that's what we did so far, dilute solution limit. For C by C star larger than 1, we expect Rouse. We expect Rouse. Why? Because of hydrodynamic screening. That's what we expect. If we expect Rouse, what is the specific viscosity? We did this. The specific viscosity would go like n. N times C, but let's not worry about C, because in terms of molecular weight dependence, specific viscosity will go like n. Okay, so we expect this quantity, expect Rouse, therefore, eta minus eta naught by eta naught to go like n. That's what we expect. So this function must be such that for C by C star greater than 1, it has to go like n. Okay, so let's work it out. How could this function give me a factor of n for higher values? Okay, so that means, therefore, I expect f eta C to the n to the 3 nu minus 1 to go like n power 1. That's what I'm expecting. This function must be like this. This can happen only if this is a power law, it's an exponent. That's very easy to figure out, right? That means C power n to the 3 nu minus 1 power something must be n. Therefore, even by inspection, you don't have to do arithmetics. By inspection, this must be equal to, right? Because I will put the answer, you'll know, 1 over 3 nu minus 1. If I put, right, if I put 1 over 3 nu minus 1, right, take this exponent and put it at the top, 1 over 3 nu minus 1, and that will kill 1 over 3 nu minus 1, multiplying 3 nu minus 1 will give me 1, that's n power 1. All right, we got it. But the concentration dependence is different, right? Not from the way we got Rouse. Here we are talking about a semi-dilute solution where the concentration is very high. We have, right, concentration very high. So what we get, therefore, the prediction is eta minus eta naught by eta naught going like n power 1 and concentration power 1 over 3 nu minus 1. That's the prediction. This is for C greater than C star. Of course, if C is less than C star, we know that result. That's a dilute solution limit, Zimm limit, where it will go like a C, and we know that it goes like n power 3 nu minus 1. Okay? So that's a crossover. And then people have worked out the crossover between how it goes from this limit to that limit with the analytical formulas. We don't have to worry about those formulas for this class. In fact, it's my work, right? it's cumbersome, technically cumbersome, but I think we need to know the limits. So we are able to get this Rouse limit. We call this to be a Rouse limit, but the concentration dependence is different from the original Rouse model. And in a dilute solution limit, we recover Einstein's law. So if I were to plot a logarithm of eta minus eta naught by eta naught, if I plot this versus logarithm of C by C star, all right, C by C star, what I'll get is, this is 1. Yes. What I will get is, I'll get Zimm law like this with a slope of 1, and then I'll have a different slope, right? This would be Rouse. That slope is, as you know, as you can tell, that is 1 over 3 nu minus 1. That slope is 1 over 3 nu minus 1. This is the Rouse limit at a higher concentration, and this is Zimm at a lower concentration. Okay, and this is a C star. Concentration becomes C. Okay. For example, right? For example, for C is greater than C star. For example, in that limit, eta minus eta naught by eta naught would go like, let's take theta solutions. For theta solutions, nu is equal to half. So I have 3 halves minus 1 is a half. That's in the denominator. So this goes like a C squared. Okay. Now, if it's a good solution, that means nu is equal to 3/5, 0.6. If it's 3/5, 9/5 minus 1 is 4/5. And then when you put it in the numerator, this will go like a C to the 5/4. But independent of whether the solution is theta solution or a good solution, the molecular weight difference is the same, N and N. Okay? And you please notice a distinct difference in this Rouse regime, which is validated semi-dilute solutions from the original Rouse model chain in infinity dilute solution. And therefore, this is what we call crossover. This is a crossover between Zimm to Rouse. That's our goal. That's what we are going to do. Now, in addition to the viscosity change, we can do the same argument, same scaling argument, which I don't need to do. You know, the way we did it here, we don't have to do that because you are, I think by this time, you must be an expert because we did so many scaling arguments when we considered semi-dilute solutions before. But I like to illustrate, at least I like to share with you the results for diffusion coefficient, center of mass diffusion coefficient. Okay. Let's talk about center of mass diffusion coefficient, the rest of today's lecture. So if I have a collection of chains like this, see, I have a lot of chains like that. This is interpenetrating like that, right? And then let me mark one of the chains in here like that. When I talk about diffusion coefficient, there are 2 diffusion coefficients, okay? One is called tracer diffusion coefficient. Sometimes it's called a self diffusion coefficient. I'll call this to be DT. That means this is going to measure, you know, we can make measurements. You can put fluorescent probes, you know, you can deuterate them, you can watch them specifically, right? This is going to measure how this red chain moves around. So I'm labeling this red chain as a tracer. And how does it move around? What is its center of mass motion? Okay. This DT, I can write in general, this DT is equal to, we did this already for Zimm dynamics, right? KBT by 6 pi eta naught RH, hydrodynamic radius, times some function of C by C star. In general, for the crossover. Okay. And then we expect, for this one, we expect for C greater than C star, we expect Rouse. That means we expect dt to go like 1 over n. Remember the columns that we did, summary we did, right? D center of mass, according to Rouse, is 1 over n. That's what we expect. Okay. So therefore, if that's the case, we expect that. Therefore, we do scaling argument. You could take this scaling argument as a homework problem yourself, do scaling argument as above. As above, similar to many exercises we did, and that gives you your dt going like dt going like, right? Let me copy the answer from my lecture notes. dt goes like, in a dilute solutions, of course, it goes like 1 over n to the nu for c less than c star, that's a Zimm. But here, it goes like n to the minus 1 for c greater than c star, because that's what we are putting in as an input. The concentration dependence in general goes like concentration for 1 minus mu divided by 3 nu minus 1. Okay. And that is for a tracer diffusion coefficient. But this is not what you measure in experiment like a dynamic light scattering. In dynamic light scattering, as an example, you are not measuring a labeled chain. What you are measuring is a concentration fluctuations, a collective. That is, I don't have any regard for whether it's a red chain or green chain or a blue chain. There is some, how do the concentration, local concentration move around, diffuse around. That is a collective. That is, how does this happen on an average, right? How does happen on an average for a single chain, right? This is a collective effect. So that's called cooperative, because all monomers coming from different chains are cooperating. So this is called cooperative diffusion. Cooperative. Sometimes in the literature, it's called a mutual diffusion coefficient. And let me give a symbol DC. Okay. And as you can imagine, if the concentration is low, this is going to also be a function of the C by C star. But if C is much less than C star, that is infinitely dilute solution, that cooperative diffusion coefficient is the same as the single chain diffusion coefficient. This is KT, because there is nothing to cooperate with, because it's all on its own. 6 pi eta naught RH times this function. But this function will be a different function. Okay, so let me call this function with DC in contrast to this function for dt. Okay, it's a different function. And what do we expect? For C greater than C star, we expect, right? The cooperative diffusion coefficient would not care about molecular weights. Just exactly the way we talked about the correlation length in a equilibrium situation, semi-dilute solutions. Because whether I have, I'm looking at here or here, the molecular weight is not important. So I expect DC to be independent of molecular weight. Because they are intermingling, I'm looking at concentration fluctuations. I'm not looking at one polymer chain, on an average of how these molecules are behaving. If you do the scaling argument, then the answer is, all right, you write this as an unknown function of C times n to the 3 nu minus 1, and I want to match that with n power 0. Take this as a homework problem. If you do that, what do you get is DC turns out to be is equal to KT, right? Let me write it down. That goes like DC goes like, again, 1 over n to the nu. That's what we have to start with for C less than C star. And for C greater than C star, This turns out to be concentration power nu divided by 3 nu minus 1. No molecular weight dependence. But you have seen this quantity before. See, nu to the 3 nu minus 1, even today you saw that. C nu to the 3 nu minus 1 is 1 over correlation length, right? C goes like this, 1 over correlation length is this. Therefore, what you get is this quantity is actually, this is actually 1 over correlation length. Therefore, we get a very interesting result. Therefore, what we get is a DC cooperative diffusion can be written as KBT divided by 6 pi eta naught times C. So in a dynamic light scattering, in semi-dilute conditions, what you measure, the diffusion coefficient you measure is actually a measure of the mesh size. Now, the quantity that is diffusing around is not the single chain, radius of gyration, but is actually the correlation length. Okay, so this is, I would call, generalized Stokes-Einstein. Generalized Stokes-Einstein. For semi-dilute solutions. And what is remarkable here is this. Please go back to this cartoon. When this red chain is moving around, I'm looking at the tracer diffusion coefficient, tracer movement, right? Tracer chain movement. When it's moving around, it's going to be slowed down. When I make this red chain longer and longer, the diffusion coefficient will be smaller. That's what we see. Diffusion coefficient will decrease when I increase n, because 1 over n. But on the other hand, if I look at the cooperative diffusion coefficient, you see entirely different picture. Because as I'm telling here, correlation length becomes small when you increase the concentration. We know that. Correlation length is becoming smaller and smaller when you increase the polymer concentration, as captured by this formula. If this, when I increase the concentration, C becomes small, that means that D becomes higher. So when I increase the polymer concentration, the cooperative diffusion coefficient actually increases. Okay? And now this is seen. This is seen. So I'm going to share with you. I'm going to stop sharing here, and I'm going to share. This is in the handout that I gave you. I want to share with you the experimental data. Okay, I'm going to stop sharing here, and I'm going to show from the handout, a figure from the handout. Okay, so let me go back. Please look at the data. This is experimental results. Okay, and here is a reference. This is how tracer and cooperative diffusion coefficients depend on polymer concentration. Right. And I showed you, going back to the note, we'll go back. For a tracer diffusion coefficient, when you increase the polymer concentration, tracer diffusion coefficient decreases. And the prediction is half, right? dt went like C to the minus 1 minus nu divided by 3 nu minus 1. When you put for a Gaussian chains, for example, right, that becomes a half, minus half. So this is a tracer diffusion coefficient. It comes down. And these are for different molecular weights. And if you, in this limit, when you look at this, this is one molecular weight, this is 78,000, and this is a molecular weight of 754,000. When you increase a log plot, right? When you increase the molecular weight, it comes down. It obeys Rouse law, n power 1, n power minus 1, d. And then it decreases. Remember, uniformly it decreases with polymer concentration. And the slope is minus half as predicted by the scaling argument we did. Now, if you look at the cooperative diffusion coefficient, it increases. And in fact, we can show that increases with what we expect. It increases with the slope for, theta conditions and good solvents, the same exponent. DC goes like 1 over correlation length, and the correlation length goes like concentration power, like minus nu by 3 nu minus 1. Okay, so the cooperative diffusion coefficient increases and the tracer diffusion decreases, and the slopes are in agreement with our predictions so far. So in the next lecture, I like to pick up why do we have a slope of negative 1.75 for higher concentrations? This is even more constant. There is a break. As you see, there is a break here. You have that slope, and suddenly there is a transition into a slope of minus 1.75. So that's our, why do we see that one? And that's the beginning of our next lecture. Okay, so I'm going to stop sharing here, and I come back